double T's are kind of a unique product with having a capability of having a very long span. When you start talking long spans, you're talking 60 feet plus, and sometimes goes as high as 120 feet.
The typical day of a pre-stressing plant usually starts very early in the morning. The product from the previous day's casting has cured by now, and the pieces need to be stripped from the form to get ready for
That's what they
today's
did
casting.
previous day, so they're taking it out now.
For any pre-stressing plant, it is very important to maintain a clean plant. Maintaining neatness is not only positive from an image standpoint, but also from a safety standpoint, since any debris that might be left over from the day before could create a tripping hazard or other safety problem. The first part of the process is setting up of the form.
So that's
A
the
thorough cleaning of
trench
the
in
entire
which the
form
concrete
is
stand is
done
going to
with
go,
basic
right?
labor and appropriate cleaning equipment. Setting the side forms, or in the case of a typical double T, the forms may be fixed forms with an appropriate draft
We're
to allow for
making
easy
many of
stripping.
these in one line.
Once the bed
Hundreds
is
and hundreds
clean,
of feet.
it's ready for setting up today's cast.
So this is the joint between
This
one T
particular
and the
bed
next T.
is
and
set
so
up
on.
for 5 double Ts, each about 60 feet long. The bed has a total length of 400 feet. This is a self-stressing form, where the form itself is designed to take the total pre-stress force in compression, and also to handle the eccentricity of the strands.
So this is
Sometimes
pretty
the
rigid.
producer
It
may
has
use
to
a
take all
form that
that.
is set between bulkheads that are built right into the ground. The pre-stressing force is then resisted entirely by the bulkheads and their foundations. Next, the strands are placed in the form and extended from end to end. Crew members thread the strands through each of the dividers and then run them through the stressing plates at each end. The typical spacing of the strands is approximately 2 inches.
This is where you harp it up and down, so these boxes will
This divider
put it
is a
at the right
steel
place.
device that separates the individual double T units from one another. A gap of about a foot is typical between the ends of the adjacent pieces. This gap is required so the strands can be accessed and cut, and that each double T can be stripped from the forms. The next step is the tensioning of the strands. In this case, we have a strand pattern with straight strands of 6 strands
These are
in
the
each
wedges
stem,
that hold
as
it in
shown
place.
here.
Right?
The strands are first tensioned to about 2 to 5 kips based on the gauge pressure reading. In this
They're
case,
so small
a
that
mark
you
is
don't need
made
one
on
like
the
that.
strand after the preload is applied. The strand is then tensioned to the specified level and is measured using the gauge pressure on the hydraulic pump. The QC technician then checks the elongation against the theoretical
Because
elongation.
your stress and
The
elongation should
requirement
match,
that
right?
is the force on the gauge
You're
and
checking
the
out the length,
elongation
make sure
must match
it's not
within
just the meter, but
5%.
also the length
If that
consistent.
tolerance is not achieved, the reason must be established and the strand may have to be detensioned and retensioned. After the strands of this double T are all stressed, the remaining embeds are set in place. These include stem reinforcing,
These are some shear
lifting devices
reinforcement
that
and
will
all
be
that.
used to strip and handle the piece, forms for blockouts in the flange, and forms for blockouts in the stems. Flange
For lights and
reinforcing,
conduits and what have you,
and
everything is
flange
into this.
connectors or vectors along the edges. In this case, one of the double T's in the bed has typical flange connectors applied along one edge and special flat plate connectors applied along the other edge to accommodate connections across an expansion joint. The form is now ready to have concrete poured, but only after a pre-pour quality control check has been made and the QC person signs off on it. This QC check can also be done by the bed superintendent and depends on the particular
This is
plant's
embedment
practices.
to attach something
Either way,
here.
the
so
check
this
is
doesn't
critical
pull out
to ensure an
and
end product with the highest quality.
There's all these things you look for, the mesh, you look for anything that could be touching the stems on the bottom. Like
Now this guy
white
may
ties
not be an
that fell in
engineer,
there,
but
is
he
that what
knows
we call
enough
some type of rubber
to handle
spot?
this.
You check the length, you want to make sure that the gaps are correct. Do we have the strand stripped properly? So there are a lot of critical things that you need to verify.
Concrete is mixed at the batch plant under tightly controlled conditions. The cement is supplied using tanker trucks. Here, the cement is being blown from the tanker through piping to the cement
It's
silos.
like a, really a factory, the whole
When
thing is like a
needed,
process.
aggregates are delivered to bins in the batch plant. The aggregates are stored outside of the batch plant in separate bins. In this case, an enclosed vertical bin system is utilized. During winter, in northern climates, the aggregates must be heated to get them to flow properly through the batching system
watch the
and to
temperature.
maintain proper concrete mix temperatures. Payloaders are used to shuffle the materials to the conveyor belt. Computers are used to proportion the materials for the desired concrete mix. Cement, sand, stone, water, and admixtures are measured according to signals from the computer.
Admixture is where it makes it really easy to flow, so you don't have to work as hard. So this is part one, then it tells you about how the concrete is placed and cured and all that comes. So this will have another ad or something, I may have to skip that.
There's gonna be nothing here if things don't change.
Computers are used to proportion the materials for the desired concrete mix. Cement, sand, stone, water, and admixtures are measured according to signals from the computer. After the concrete is mixed, it is discharged into a delivery device. It's imperative that the concrete mix be delivered to the form as soon as possible. These vehicles are called tuckers, and they are used to deliver the concrete to the bed in the yard. A self-consolidating concrete
That's the
is
key
being
word,
used to cast these
self-consolidating.
particular double T's.
So you're ready to go.
With this type of concrete, vibration is not required to consolidate the concrete. However, minor controlled vibration is used in the double T stems to help remove air from the sides of the form, reducing bug holes in the stems. There are many advantages in using this type of concrete.
We do use self-consolidating concrete for our
I guess
double
this is
Ts.
like PE after all.
We feel that it gives us a better
Quality
finish. We feel that it's easier to place, takes less labor, less strain on the labor to place that concrete.
The QC department will make the necessary tests at this time, including a temperature check of the concrete. Since SCC is being used here, a spread test is done to check
This
the
is
concrete
as opposed to a
flow
slump
in
test.
lieu of a slump test. The spread is measured to assure conformance to the planned spread. The edges of the circle of concrete are also inspected to check for segregation. The appearance is translated to a visual stability index number. There is a check for air content. Cylinders are filled and will be used later for strength tests of the cured concrete. Back at the bed, the concrete placement continues. A vibrating screed is used to level the surface evenly. A bull float is used to finish the surface. An evaporation-reducing spray is also being applied to the surface to minimize the potential for plastic shrinkage cracking.
A lot of
The final
mechanism,
finish will
mechanics,
vary depending
a lot
on the
of,
use of the double T.
You don't have as
If
many
a
people.
cast-in-place
if you have
topping is
equipment.
necessary, the surface will be made very rough so that a good bond will be achieved. If it is a roof, the finish will be
This is a
relatively
brush
smooth,
that
but
makes
not
it rough on
necessarily
top.
perfect.
So
In
you
this
don't
case,
slip,
the
if
surface
you're
is
driving
brewed as these double
tire,
T's are being
like
used in a
this.
parking structure. Different patterns can be applied depending on the needs of the project. The bed is now in its curing stage. Sometimes, particularly in cold climates, the double T may be covered with tarps. In other areas, they may be open. Accelerated curing is often
This is
done
the
using
steam
live
curing
steam
or,
or radiant
get it
heat
fast.
from heaters attached to the form itself.
Double Ts for parking garages really need to be held to a high standard. When they're assembled in a garage, they make the finished surface. There are tolerances for putting these pieces together, offsets in the surfaces. All of the connections are very sensitive as well. To be executed properly, the embedments in the double T have to be placed properly. So there, again, are a lot of
So it's a
critical
cyclic thing.
issues
Every day they
that
do,
you have to
next
be
day they come
concerned
back,
with to
take it
get
out, the
proper
following day pour
performance
again.
out of that simple
Just
double T.
keeps on going.
After 12 to 16 hours of curing, the T's are ready to be stripped. The QC department first tests the concrete to be sure it has achieved the strength required to detension the strands, typically 3,500 psi. This is a typical test being conducted.
So now you can
The
transfer
strands
the
are
pre-stress at that
detensioned
point,
in a
right?
specific sequence established by the
It's
QC
cutting the
department
bars so
or the
that
plant
they could
engineer.
become independent units.
Here, personnel are positioned at each end of the bed and at some of the intermediate bulkhead locations. On a signal, they burn the strand at each end. After all the strands are cut and block-out formwork has been removed, the T's are stripped from the form. Cables are attached to the lifting devices, and each piece is removed and transported to a detailing area for any minor cosmetic touch-ups. Also at this time, the QC department does a post-pour QC check on each piece that is
QC
brought
is
to the
quality control,
detailing area.
QC, right?
When I first get back there, I go and check the length of the piece, verify that within, there's a tolerance of probably a quarter inch or so. Check the width, we check the vectors, we check the electrical blockouts. I do a visual for any type of discoloration in the stems
Now,
underneath.
shrinkage is beginning to
Any type of,
happen, but he's
surface
checking at the
cracks,
beginning.
bug
He came back
holes.
after 6 months,
Just do
his
complete
length is
visual.
not the same, right?
Any defects are noted so that repairs can be done before shipping the T. After all the work is completed, the double T's are moved into the storage area where they are typically stacked using appropriate dunnage located near the ends. When the job site requires the T to be shipped, it is
There's no-
loaded on a
nothing in the
trailer
middle, right?
and transported to the job
Nothing
site.
in the middle of the span because you will mess
What
up
you have
the
just observed
the
is
strand
the
is like a
process for
drape,
making one
right? So
type
you don't
of
have
pre-stressed product.
couple of those.
These other types are
Bending
made using
moment has to be
essentially the
maintained.
same process. Hollow core plank, which are used for floor and roof components in multifamily housing, schools, hotels, and many other entities. Inverted T-beams, which can be used in any total precast concrete build system. Columns, which are cast horizontally and then rotated in the air at the job site.
This is what you
They
do
are
for
often
parking
designed as
garages.
pre-stressed
The
components.
one down the road at the hospital is built. with
Architectural
wood.
spandrels used in office buildings and parking structures
Yeah,
can be
there's
made
connectors,
using the
bolts,
pre-stressing process.
Keep it in place.
Deck slabs and box beams, which are used primarily in short span bridge construction. Standard
That's for
ashtray
Benny, right?
girders, which are used in long span
This is
bridge
fun.
construction. Standard bulb tees are also used in long span bridge construction. Pre-stressed piles that support any type of building in areas that have unfavorable soil conditions. As you can see, there are many types of pre-stressed products available. The variety of products that can be pre-stressed in a long line operation is almost unlimited and is up to the
This is the highway
imagination of the
department
design
stuff.
professional.
That you would use for.
We
bridges.
really do encourage our customers and architects and engineers to get to our plants to really understand how precast concrete is made. They need an understanding of the high.
To see this in real life is even
quality
better.
out of precast
At least we
concrete,
got this.
as opposed to the random quality that you might get out of cast in place.
We have one plant
Well,
in
it's important
Lexington.
that we do things
Yeah,
as
Lexington.
efficiently as we can and as cost effectively as we can, but also as well as we can. And it's not only my responsibility, but the responsibility of everybody here, management, labor, everybody included, to do the best job that they can to, at the end of the day, make a little bit of money, but also have a customer that's very happy and will possibly want to have some return work coming back our way.
That's the product. I say thanks. And that was good. I liked it. I saw quite a few. I thought that was good. There's one more for pre-tension bridge beam. We'll see it next time. I think let's continue with what we were doing. So it gives you some idea, better feel for what we are dealing with. Minimum stress or maximum stresses per ACI. I think that's the next topic. if I'm not mistaken. Yeah, that's where we were. So, the simple thing to do is to go to the book and look at what are the allowable values. So let's see here. So look at this fast. chapter 2, you have this section 2.8 that talks about all the allowable values, ACI maximum permissible values. Let's see, someplace there is oh, there it is. You can see things more clearly. So these are the symbology. FPY is the specified yield strength. So F is for stress, P for pre-stress, and Y for yield. So this is for, as compared to for regular concrete, you simply write FY. So FPY is for pre-stress. And then FY, specified yield strength of non-pre-stress reinforcement. FPU, which is the U for ultimate and P for pre-stress, is the specified tensile strength of pre-stressed tendons. Tendon is the wrong word. It should be strands or wire, right? And F prime sub C, just like ordinary concrete, is specified compressive strength of concrete at 28 days, right? And then F prime sub CI is the initial strength when you transfer the stress to concrete from wires. So these are our symbology. Once you know these 4 or 5, then it becomes easy. So for example, extreme fiber stress in compression is 0.6 F prime sub CI in the initial stage. So for example, in your assignment, if you were to check the initial stage, then you would use 60%, and if you knew this value, right? But we don't know in our case, so we don't know what was allowable, right? Extreme fiber stress in tension, except for C, is 3 times F square root of this number, F prime sub CI, which is around 4,000 or 3,000 PSI, right? So that's 3 times that. But if extreme fiber stress in tension at end is simply supported member, then you go twice as much. So depending on what kind of member it is, you allow 3 or 6, right? Then this is the initial condition. Then this is stresses in concrete at service load, which is the final condition. Then you are different numbers. This you have used 45% of F prime sub C, 2,700 for 6,000. This one is 0.6, is the extreme fiber stress in compression due to pre-stress plus total load if the live load is transient. If the live load is non-transient, then you go back to this. Live load is usually transient. People are walking around, there is snow, there is other things. They are come and go. If you are, what's the reason? What's the differentiation? If you have a sustained load as opposed to transient load, then the creep and will be affected, right? So you want to reduce it. So that's why you want to differentiate between transient and non-transient. So if it is sustained dead load and live load are large part of the total service load, then this is the extreme. If it is if the live load is transient, then you go 60%. So watch out which kind of load you're dealing with, right? And then the extreme fiber stress in tension is same as that, except the last part. Except you will allow 12 times or 2 times this if you do all this, which is extreme fiber stress and tension in pre-compressed tensile zone of members, except two-way slab systems where analysis based on transformed crack section and bilinear moment deflection relationship shows that the immediate and long-term deflections comply with ACI definition requirements and minimum concrete cover requirements. Usually it works. Usually you have cover and a few other things, so usually you go this, but sometimes if you're careful about cracking and all, you go back to 6. Right? So this will be specified by the code. And then here's the steel part. So this is the concrete initial, concrete final, and this is the steel. So tensile stress and pre-stressed tendons or stress, it should be wires and strands. Due to tendon jacking force is 94% of the yield. So that's how much you can go, right? So it's almost 180 KSI out of 189 for grade 270, right? So that's very high. So the reason being, it doesn't have a plastic plateau, right? Reason being, if you don't take this kind of chance with regular steel, why would you not? So, because in regular steel, you're teetering to fail, right? Or not fail really, but in a regular steel, you go like that, right? In a regular structural steel, for example, your stress looks, or your strain looks like that and strain hardening, right? So you don't want this to happen because this is 10 times more than that and you will suddenly have a big sag, right? In our case, we are going like this. So even if your 1% is here, you still have a long ways to go before you keep on going. So there is, you can go 94% and not have a huge problem if you are slightly off. So you can take the risk, that's why you're that high. This is immediately after pre-stress transfer, but not greater than, what's the difference between this and that? Like, this is the stress you apply when you pull the wire or strand, right? Then as you release it, you're losing right away. So then you get down to this, right? So remember we saw the abutment, it's very rigid and yet it gives a little bit when you apply the load. So
Literally, the 0.94 is that, like target strength. Okay, the target strength, because you have to go beyond a certain amount.
No,
Assuming when you release, I lose this much to attain what I want, which is that.
So at that stage, when you immediately lose, so there are two losses. One is called immediate loss. As you cut the wire, you have immediate loss. Like the guy was taking the torch and cutting those strands. So you have immediate shrinkage because of elastic shortening of your beam, right? Because any material that you put compressive stress will shorten. We can call that elastic shortening. And what's the other shortening? Shrinkage and creep. That will happen over a long time, right? So we want to keep track. So this is after the immediately after transfer, as soon as you cut the wire or put the wedge, right? Either way, you're reducing. Then you come down to post-tensioning tendons at anchorage and couplers immediately after tendon anchorage. So if you have couplers where you're tying two wires together, you want to be even less. Okay, this is for post-tensioning. So that's the other one. So depending on what you're dealing with, the stresses are different. Now these are ASTO, those were ACI, Concrete Institute. This is ASTO, which is another word. So these are a little different, but similarly, right? You have values for the initial and final stage and concrete and tendons and all that, right? So these are the limits, and the right-hand side is the mean. I have shown you this before. So if you're looking for humidity, then you go to this chart and find out where you are. Okay, so back to this here. So what is pre-tensioning procedure? We already looked at the video, so we are knowledgeable already, but let's go over here. So number one is steel wires and strands are laid, right? They are simply stretched, like the guy was taking with a cart, right? Just laid.
Just before we go to pre-tension, now when you lay on the tire, for example, I'm doing monitoring on my structure, so I want to, but of course over the years it has been losing, it has been
Pre-stress.
losing, pre-stress. So when you like it, that I have to do post-tension. When you like it, at what point?
Oh, the post-tension is another method of applying pre-stress. So there are two ways you apply pre-stressing force on concrete. This is one of them. It's called pre-tensioning. This is done one time. You cannot come back and redo it again in this case.
What I'm trying to mean, like we can add more stress, more pre-stress in that.
Not in this case.
Okay.
This is locked in. Remember the double T you saw going over the truck? Well, that you cannot do anything. It's just done forever. You're only going to lose. There is no gain. You can't gain anymore. You can't go back and tighten anything. There is nothing you can do here because it's all bonded. Now, if you try to stretch it, you can't because it will just fail the ends, and between the wires and the concrete, nothing will go in the middle part, just the ends, few inches. That's all you can stretch, right? If you're lucky. Otherwise, nothing will happen there. You can't break the bond. In post-tensioning, before you put the grout in the duct, you can still do it. Once you put the grout in the duct, which we'll talk here in a minute, you can't do it. It's like just pre-tensioning. So there are two methods, like I was telling you. This is the first method, which we just saw the demonstration of, right? So, you see the strands are laid, and then for hard tendon profiles, the bed is provided with hold-down devices, right? So that is shown in your book. I think, yeah, there. See, this here shows how your heart up and down. You have devices here to push down, devices to push it up here. Like the guy was carrying the box to keep it up and down. Depending on what you need, the box will do it, right? Just keep it at the right place. So you do this one. After you lay it in the place, then you put these things, devices, to keep it up or down, depending on the bending moment diagram, right? You follow the bending moment diagram. You understand? So this one is for a concentrated load. This is for two loads. Just follow the bending moment diagram, in other words, right? And if you want it draped, then you know it's a uniform load. Depending on what you need, you can change the profile, right? Okay, so if I go back to this here then, so for hard tendon you do this. The bed could be several hundred feet long. We just saw that, like we have 400 feet long in this case, right? And pre-tension is achieved by stretching all the strands at the same time. Key, this is a very important sentence right here. So you're pulling all wires together like you know how you can pull so many strings with all your fingers. You're pulling with so many jacks, all of the wires together in one stretch, right? You could do one at a time, but that's not what is done here, right? So in other words, you're running one hydraulic machine. All the jacks have the same pressure, so they're pulling together, right? Unless it is done that way, you cannot be assured. If you have 2 different or 5 different machines, one machine or one pump for each jack, then you don't know, the pressure will be hard to maintain. One will be ahead and one will be slower, but you want it all together. So you pull it. So pre-tension is achieved by stretching using jacks all stand at the same time. So multiple jacks on one hydraulic pump, right? Concrete is placed. You're stretched, you keep it stretched, right? And then you pour the concrete like these guys were doing self-consolidation. You just pour it up. Prestressed concrete is placed and allowed to be cured until desired strength is achieved, which is the next day if you do the steam curing, or if you don't do steam curing, maybe 3rd day. You'll get your strength, which is about 60% or so, right? So for 6,000 PSI, you're around 3,500, you will say, okay, I'm good, right? So pre-stressing tendons are cut at that point. Now you have individual units that you, like a cookie cutter basically, right? And then the bond between the pre-stressing steel and the concrete transfers the force into the compression, as a compression in concrete, right? So you have an elastic shortening right away of the beam, and the wire will be slightly smaller. Lose some pre-stress, in other words, right away, right? Okay. Let's see what time we got, 8:21, I think we have time. Let's try this one. I think this was interesting also. Let's see here. I hope I got the right one. This is a private company, so we are really glad. This other one was private too, but they have a good music group. This is another 5 or 6 minute long. This guy's a little more into theory, so.
Okay, now here's our typical stop end that would be used to orient the pre-stressing strands that we would use to apply that compressive force to the beam end. Now note, these strands are not tension, they're slack, so there's no danger here. You must be very, very careful with fully tensioned pre-stressing strands.
See, you see there are 3 wedges, 1, 2, and 3,
force that can be
to
contained
grip
in
the
each
wire,
of the
you know,
strands.
as you go inside.
This particular strand, in
It's
fact,
really easy.
we would actually tension up to a load of 209 kilonewtons. In just one
There you
strand.
go, kilonewtons.
So what we would do, these
I don't know, I have
strands
any
would
feel
be
for what that is.
jacked up. They would be pulled back. They would be essentially stretched. They would be put into that very large amount of tension, 209 kilonewtons for these. The concrete would be cast around the strands into the appropriate cross-section. Once that concrete has reached the specified strength, specified compressive strength, then the strands would be gradually released, thereby transferring that force.
This
that
guy
was
is a
in
little
the
more
strands when they were
illustrated in
stretched
terms of
into the
mechanics,
concrete.
watch him.
So that very large force of the strands would be then applied as compression into the beam itself. Now, notice with this strand layout, there's a far larger number of strands closer to the bottom of the beam. The bottom of the beam, the soft of the beam would be just 50 mil underneath the actual bottom
You got a
of the strand,
missing
50 or 60
wedge
mil.
on the one of them.
The reason for that is, not only do we want to apply compression to the beam, we also want to apply a bending moment to the beam as a result of the pre-stressing operation. So because that overall position of the strands is eccentric, it's removed from the centroid of the beam, that enables that application of pre-stress to also apply bending moments that will counteract or act against and relieve the bending moment that results from the applied loads, the loads that will be applied to the beam under working conditions. Let's step back over to the finished beam itself and go through the final steps of the final aspects of how a pre-stressed bridge beam works. So this beam is one of our finished products. This was actually cast not long ago on this bed itself. Now, you'll notice there's a bit of a gap between the soffit of the beam and the actual bed itself. This is a result of what we just spoke about. When we apply that compressive force from the pre-stressing tendons, pre-stressing strands, not only do they apply that beneficial compressive force to the beam, but they also apply a moment that relieves the moment applied under working conditions. So this moment that's applied by the pre-stressing operation results in the beams actually cambering up. The beam will actually lift up.
Even with the
several
sulfate, it's still
millimeters, 10
cambered up.
millimeters, whatever the case may
It's
be,
ready to
depending
take
upon
more
the beam
load
and the
from the top.
pre-stressing amount of layout used. It will actually camber up. Now, this is beneficial with regard to deflection checks as well, too. Generally, for bridge beam design, we don't need to carry out rigorous deflection checks, but from an aesthetic point of view, you don't want a beam visually sagging on site. So this natural camber that results from the pre-stressing operation itself will help eliminate the potential that that beam would be visibly sagging on site as well. Finally, you'll notice as well too, we've got shear links in the beam as well. The shear links we use in the bridge beam would really be not substantially different from what would be you may be accustomed to for reinforced concrete.
That's
bridge
for
beam
the
design.
composite
So,
construction.
again, so bridge beams, pre-stressed concrete bridge beams would also make provision for shear design, shear reinforcement as well. So in order to summarize how pre-stressed, precast bridge beams
So this is
work,
going to have a slab on top afterwards,
beams are
right?
intended to carry flexure as well as shear, but that flexure that they're going to carry results in tension in one face of the beam. Concrete is not good in tension. In reinforced concrete, we use bars, steel bars, but in pre-stressed concrete design, we apply compression in order to overcome that tensile stress in the beam due to flexure. The force is applied using pre-stressing strands. The pre-stressing strands are stretched. Concrete is cast around the strands in pre-tension concrete, and the strands are slowly released, thereby applying that compressive force to the beam while simultaneously applying a moment to the beam that also acts to relieve the applied moment. I should also point out as well, too, that what I've been speaking about here relates to pre-tension, pre-cast, pre-stress bridge beam design. There is also post-tensioning post-tension bridge beams, which are slightly different, well, rather different from pre-tension bridge beam designs.
That sounds good. Okay, show some more structure, I believe. Both are pre-tension, so I thought this was post, but anyway, I'll look for one. There are plenty available online. See how post-tensioning is done. Basically, you have a solid beam in post-tension case already ready for you with a duct inside, which is hollow and has a wire, not pre-stressed. Then you come back and do the same jacking and same freezing. But in this case, in post-tensioning, you don't have the abutments. You're abutting against the beam itself, right? You're pushing against the beam itself as you jack up. That's the basic difference. And also in post-tensioning, your duct is empty, at least in the beginning. So if you lose some pre-stress, you can come back after a few months or a year, and you can jack up some more because the duct is free. You can still stretch the wire inside the duct. Well, once you're sure that you're done with it, then you can grout it, right? You don't want to wait too long because you may start corroding. You don't want to corrode. So you either can coat it, at least lubricate and put some grease on it, or you should, better yet, you put some grout inside, right? So that's post-tensioning.
I have a question. Which one is better?
Both have some plus and minus. In pre-tensioning, your quality control is better because it's all done in the factory. So you have remember there's a quality control guy chasing this all the time, making sure everything is double checked before you put concrete. In case of field conditions, all of you know there is a parallel to this in steel. When it comes to welding, it is preferred that you do all the welding in the shop. And you do minimum field welding because the conditions in the field is very variable, right? You may have dust, you may have quality issues, you may have moisture, so many things, right? So that's why you try to do it. So the comparison between pre-stress, pre-tensioning and post-tensioning is similar, that if you want quality job without any skilled labor in the field, then you will do pre-tensioning. So because all you do is put and bolt it together, right? Or pour a little bit of concrete here and there. But if you're sure that you have skilled labor available in the field, and you don't have too many products of same kind, just have one product or two products here, then it's kind of hard to do mass production. Then your factory is not as effective because you need mass production for a factory to work properly, right? So if you have hundreds of pieces, like you're making a Motel 6, right? So you're going 50 Motel 6 and you are the owner, or I'm giving you one example, or you're making a school, or you're making a big sports complex where you need many items, then you may like to have pre-tension member. Quality control is better predictability. But if you have a massive bridge where you have only 2 or 3 girders and you want to not lose the pre-stress over a long period of time, then you say, okay, I'm going to pre-stress this by post-tensioning and do not grout it for many months or a year. And then you come back and tighten it where you got most of your pre-stressing or pre-stress losses are done within a year or 2. Then you come back and tighten some more or jack up some more. And you can do that very easily. So then you can gain the best you can. Now you can apply extra load without difficulty, right? Or in case you have to, because of political or some other reason, you want to bigger vehicles or more vehicles to come on your bridge, right? So you can go back and put more or post-tensioning so you can allow bigger loads, right? So you can upgrade your bridge if you will, right? So if you want that flexibility, then you do post-tensioning. But in case of a hotel or a house or a sports complex, the loads are pretty predictable. They're not going to change a whole lot, especially in a hotel, what is going to happen. You have a couple of furniture and you have a bed and people come and sleep and you're done. It's pretty predictable. So you don't have to worry about these. You can pretty much do pre-stressing, right? So that's the advantage and disadvantage. I don't know, somewhere in there we should have had that. I don't remember if we still have it. Okay. So post-tensioning, as opposed to pre-tensioning, we can go step by step, like we have looked at a couple of videos and we have gone through the steps. So concrete beam is cast with minimum reinforcement and tending. So you put minimum amount of regular steel and pre-stressing steel to handle it from, so that these are also cast sometimes away from the site. Sometimes they are next to the site, like 50 yards away, and bring it back to where you want to support it. But in any case, you do that for handling purposes, so that you can lift it up without breaking it. So you do that, then for draped or half tendons, the tendon is provided with corresponding profile. So your duct is matching the profile you want inside the beam, right? Already done as a cavity, like a snake, right? The element is individually cast and post-tension. In other words, you do one item at a time, not 5 in line, right? So one at a time. The concrete is allowed to cure until desired strength. So this part is same. You have to still wait for the initial condition when you transfer the pre-stressing force. There is hardly any or no pre-stressing force up to this point. The concrete is pretty much stress-free, right? So now you're going to post-tensioning achieved by using jack, figure 224, one strand at a time or all stand together. We have a choice now. You can either stretch one, like you have a 10, remember in your example you had 10 strands, so you can stretch 1, 2nd, 3rd, and 4th, and so on, or you can stretch all of them together. Or you can do 2 at a time, right? Why would you not do all together? Because you need a bigger jack. You may not have that jack, you may not have the hardware, or you don't want to take that much risk in case of slippage or something happens accidentally, right? So you could use a smaller jack, but sequentially. But we will see the benefit and loss of that when you calculate the pre-stress loss because of elastic shortening. And this is important, whether you jack it one at a time or all together. Which one will be less loss?
I think the one.
That's the question. I know the answer.
I think the one. This is my opinion.
Yes.
I think the one which has been done once.
Right. Correct answer. Right. The reason is, suppose you are the first strand. So I stretched you and I released you. Now you got 189 KSI, right? Like your example is. When I put the second one and stretch it and release it, this will also have 189, but it is going to compress the beam and shorten it by a tiny amount because the first one has worked and the second one is working now. So the first one is going to see, hey, I lost something because my length is smaller now. So my strain is less, so my stress is less, right? So then the third one comes along and I'm going to stretch the third one. Guess what? The second one and the first one will see the loss, right? And so on. So the last one doesn't see anything. The 10th strand that you put and release, it won't see it see the minimum loss, right? So the first one is going to see the loss 9 times over. So that's the loss, And there is a formula to calculate whether you stretch it all together versus you do it 1 or 2 at a time. There is a formula, and the logic is still the same. That which one will be the most losing the value of stress, right? You start with 189 KSI, right? So the first one is going to lose 5% when you put the second one. When you put the third one, the first one is going to lose additional 3 to 4% and so on. Not exactly 5% because some shortening has been done, right? Okay. So the tendon is gradually, okay, now let's see. You do the larger jack and smaller jack is the issue here. So if you're a small company, you'll do one at a time. You know it's going to lose, but that's okay. The tendon is usually grouted unless there is a plan to increase the pre-stress force in the future. So after you do all this, then you have a little passageway into the duct from the side or from the top that you inject the grout. Once you inject the grout and make sure there is no cavities and all that, then you can close up the gap and cover the whole thing. You don't know what's inside, right? So it's, at that point, it looks exactly like the pre-tension member. No difference from here on forward. It's the only choice here is up between here and here. You could wait for a while if you have a plan to post tension some more. Right? So grouting is provided for following reasons. The permanent protection of the pre-stressing steel, so you don't have corrosion because you are covered with grout all around you. Right? The number two is develop bond, because if you don't have developed bond, then it's not going to behave like a in the ultimate stage, not at the service load. Ultimate stage, you need the bond so that it will act like a reinforced steel beam for a higher value, though, right? So you need those two. Grouting satisfies these two, bond as well as corrosion protection. So is post-tensioning clear? I'll look for a video, and those of you who are curious may like to go online and see how post-tensioning is done. All right, so one other thing is grouting. The problem with post-tensioning is you have to mess with grout, right? It is this is a messy work, but it has to be done. So the material is portland cement type 1, 2, or 3, depending on how fast you want, what kind of situation you have. So 1 is the slower, and 3rd is the quickest setting, right? I can't remember 2 right now, but there is a ASTM for the portland cement, A150 or C150 rather. Cement should be fresh and should not contain lumps, because that's a sign the moisture has been exposed and your hydration process has started. So you want to make sure. You don't want to have a packed set, which is hard like a rock, right? Definitely, right? Water should be potable. That means something you could use for human consumption, for example. Clean and free of injurious substances such as high acidic or all that. So you don't want to have that, because acidity could create problem with corrosion of the bars and de-stressing or otherwise. And mixtures are needed for flowability. And if you have a lot of non-reinforcement or regular reinforcing bars, self-consolidation as well as shrinkage compensating concrete, all this could be done here to reduce the amount of pre-stress loss you would like to have, right? And then the admixtures containing chlorides and fluorides, sulfides, nitrates should not be used because they attack the concrete itself. Sulfides are not good. Sulfate attacks are very notorious. Chlorides are also creates corrosion in rebars, so we need to stay away from these. So duct we already talked about, right? So the duct is the other item for grouting. So you have grouting material, you have duct. Those are the 2 items we have to deal with. Then we have these 3 or 4 other items, which is grouting, opening, or vents. So what we want to do is, if you don't have the vents, and you're simply grouting from one end, obviously you can't grout very far. We have to have other end where the material is going to pass through to make sure that it has reached the entire length, right? Where is the air going to escape if you don't have the outlet, obviously? So you have one outlet, but then you have other outlet also make sure the whole entire length is filled. There is no bubbles left in between that we don't know of, right? So you need openings and vents. All ducts should have grout openings at both ends, not one end. And you should have draped cables. All high points should have grout vents, because the air will rise up at the top, so you have a vent on if you have a sinusoidal wave of your tendon, and the high points or the support locations should have the vents, right? The grout vents or drain holes should be provided in freezing climates, because at the bottom, the drain holes will take care of the low points. In case of freezing conditions, you don't want the water to become icy later on and have problems. So you want to drain all the water, right? Duct size. Duct size should be at least twice the area of pre-stressing steel. So you calculate the area like you did 1.53 for 10. So you should have 3 square inches or more for the opening cross-section area, or a 4-inch. In your case, a 4 or 5-inch duct will be pretty good, right? So that's how you decide. For a single element system, the duct should be 1/4 inch larger. So if you have 1 bar or 1 strand, and that's what that is. Placement of ducts. Where do you put these ducts? An inspection of the duct should be made for any damage after all the reinforcement forming and ducts are in place. So the duct is a thin gauge material. So, and it needs to be thin gauge because if you have thick gauge material or thick metal, it won't bang into the shape, so you want to be thin. But the problem with that is that you can poke holes, which you don't want poke holes or damage shape. Because if you damage the shape in place of a circle, if you become egg, then you may not be able to pass through your strands, right? So you want to keep the shape, so you want to inspect it. Damage after all the reinforcement and forming is done, so nobody has done any damage afterwards, right? So you looked at all that, make sure there is no pinholes or damage or anything, right? Then you say duct should be secured in place to avoid movement because you're going to vibrate possibly, you're going to walk around, you're going to scream, you're going to do all these things, activity. So you want to avoid that movement because now your profile will be messed up. You want a certain profile, exactly what you want. So you want to hold it in place, secure in place by wires or various means, right? Similarly, the grout opening should be secured in place because if you don't, then you will not have the advantage of the highest point or the lowest point. So you want to make sure they don't get messed up. So the placement, the duct size, and the grout opening locations are important. All this is because we want to have perfect bond and we want to have least amount of corrosion. So you don't want to have any water trap or air trap, you want only grout inside, right? That's the reason. Okay, we are getting there. So this is the common way of grouting now. Once you have all this hardware in place, the duct, the vents, the inlet, the outlet, the material, the cement, the water, all is decided, you mix it up and you pump it basically. Ducts with concrete walls should be flushed to ensure concrete is saturated surface dry, SSD. So what you want to do is, if you have a cored hole, not metal, then if you make it too dry, then it will absorb some moisture from you, make it hard, right? So difficult to move. And you will change the property, water cement ratio will be different than what you intended. So you don't want that, so you want to flush it with water, put enough water and make sure it is saturated surface. All high points should be open at the start of grouting. So you have all these high points, like a wave, assuming that you have multi-span bridge in this case, right? Or multi-span beam rather. If you don't, then if it is a simple support beam, then you have only two ends that you have to worry about, right? You don't have a high point other than the ends. So at high points, vents should be open at the start of the grouting. Then start grouting with a pressure not to exceed, so you don't want to damage the duct or the concrete or anything else. And allow the grout to flow from first vent until residual water and any entrapped air is released. So you're moving from left to right, for example, then you will have all these vents will start spilling over the grout, right? From one end, you spill over, second end, and you keep closing them as you see all the air and all the water has gotten out, right? So you start doing that. Cap or close the vent first vent. So when you see the grout with air and water has come out, and you're going to waste a little bit because you want to make sure there is no water left inside that might be trapped, or there is no air left inside. So when you see the grout is flowing with no air and no water, no free water, and you cap it. You just put a tie on this or you cap it somehow so no more comes out of there. And in the same sequence, close the remaining vents. You just keep going along the length and keep closing this vent as you see the grout is clearly flowing, no air, no water, right?
Where is the first vent?
Yeah, so you're starting, okay, so you have multiple vents. This procedure is assuming, because this is a generic procedure, so it's assuming that you have a beam that has a profile like that, say, right? So you have a vent here, this is vent number 2, this is vent number 1. And depending on the spans, you may have more than 2, right? So this is your first vent. So you are pumping grout from here. And this is the other end, right? So this is vent number 1. So you pump, the grout is moving like this. then you watch this one first. So let it spill out, right? It's going to start spilling out like, how you sometimes you gargle, you have air and water coming out, so it's going to make a little noisy scene, right? And so air and water is coming out first, ahead of the grout. As your grout is pushing, the air is going to come out, right? And pretty soon you'll see that air is less and less and more grout. And then when you see pure grout, then you cap it, close the valve. You have a little valve on it, or a rubber band or something, close it. Close the tie, in other words, right? So you close this. Now the grout is moving, and this is still spitting out air. Air is coming out, right? But as the grout proceeds, you'll start seeing some grout and some air mixture and some water mixture, depending on what it is inside. If it is all air, then there is no water, of course, right? So when you see that the air has stopped and the water has stopped, then you close this vent. Then you watch this last one. This is not a vent, this is the outlet. So let's see what we say here. The rate of injected grout should not be less than, I forgot the B, less than that of the injected grout. So this flow rate should be the same as that, or you have some cavities left here, right? So you watch this flow to match this flow. If it is not matching, less is coming out, that means some air has to pass through, right? So it's like the GI tract of our body in a way, right? So you have to watch out the other end. So now once you see the outlet is also spitting out only pure grout, and there is a lot of mess, right, because of all this, then you close both of these, on this end as well as that end. Now you're all grouted. You made sure that there is no pockets left of water and air, right? So this is a pretty sequential method, right? When one-way flow of grout cannot be maintained, which is from left to right in this case, and the grout is spitting out back flowing where you are trying to inject, then there is a problem somewhere. It's not moving. There is an obstruction. The tendon has been crimped because of damage, right? So it's not moving. So when one-way flow of grout cannot be maintained, there is the obstruction or insufficient pressure, because hydraulic flow, you need some pressure, right? So if there is not sufficient pressure, then it won't go over this because of the hydraulic gradient, right? So you need to, the grout should be immediately flushed out because you have a problem. You need to go and inspect what's going on with your tendon profile. Is there, send a camera maybe like a snake, find out. Just like the doctors do, right? They check your arteries and veins, check it out, see if there is a blockage. So you check this out, then in below freezing temperatures, ensure ducts have no water to avoid freezing. That we did in the beginning also, especially in low temperatures. Right? Keep concrete above 32 degrees Fahrenheit from time of grouting to 2-inch cubes of grout to 800 psi. So you make sure it's warm enough, so it's not freezing. Make sure that stays warm. Grout should be under 90 degrees during mixing or pumping. If required, mixing water could be cooled down. If the temperature is too high, then you make sure it should be under 90 degrees so you don't get too hot a mixture, right? Because that will affect the quality of the material. Okay. So the last thing which I wanted to talk is 10 principles. This is totally unrelated topic, but it's one of my favorite. So I thought, especially most of you are just barely out of school. So in general, for engineering practice, these 10 principles apply. Not necessarily grouting or civil engineering or post-tensioning or pre-tensioning. In general, anything you do in engineering, not necessarily civil engineering, any engineering effort, and in fact any effort for that matter, but some of them are specifically to engineering. So you cannot have everything. What does that mean? If you're asking what's the disadvantage, well, there is everything has a disadvantage and advantage. So make sure you don't say I'm going to be perfect here, because you will have something that is going to drag you down in terms of one. If salesman says this is the perfect question, again, something is wrong, right? So you cannot have everything. I cannot have the highest quality and the lowest price, in other words, right? Something is wrong with that phrase. So I can't have both. You cannot have something for nothing. So if you want a freebie, one has to pay something to have a free gift. There's no free lunch, they say, right? So you got to give up something to get something, right? In other words, in design, for example, you want to maximize the quality, you better be prepared for some cost, right? Can't have free. It is never too late to accept your mistake, for example. If you realize you're designing something or you're constructing something and something fundamentally is wrong, that means, for example, you're putting a very simple example, you're putting a foundation, and then on the top of the foundation there's going to be a building, right? And you realize while you're doing this, your mistake or somebody's, that the excavation level itself is wrong. It's wrong by a couple of feet. And you don't say anything, guess what? You will have problem, right? Fitting the building will not be at the right height, something is going to go wrong, right? So, and depending on the process, you may have a very serious problem. If it is a hut, who cares? A couple of feet is okay, I'm going to live in my hut. Problem is there are other things. You're going to have water flowing into your building, going out of the building, your sewer will be, manhole will be too high for your building, whatever, right? So you have to deal with other things. It's not never too late. Change in design or construction, under construction, structural construction, accept the mistake, accept the deficiency as soon as possible. But if you're late, still do. Don't say, okay, I'm going to do it tomorrow. It's never too late. That doesn't mean that you will wait, but it's correct. Accept it, because it will come and catch you pretty hard. Change principle of practice in light of new knowledge or experience. So you don't say that, okay, I know what I'm doing, because things are changing. Even sometimes the theory itself that changes, right? So you want to make sure you are staying up with. There is no progress without risk. So if you make a decision and I want to be risk-free, there is no such thing. There will be a minor amount of risk in everything. Right? So your design cannot be foolproof. I don't want to build an agricultural farm with the code of nuclear plant, for example, because nuclear plant is risk-free, practically speaking, right? But then you don't want to put that in a farmhouse where you're raising chickens or vegetables or something, right? Because the risk is smaller. So you don't want to have without risk. You've got to manage the risk depending on what it is that you're dealing with. The proof is in the pudding. The idea or concept requires testing. In other words, you might have a bright idea, but let's make sure it's practical. It's going to be done. Simplicity is always advantage, but be aware of the oversimplification. So I said, nah, it's too complicated. I'm just going to make, this is a simple beam. It's not a simple beam. If it is not, then you better accept it. If it is a multi-span beam and I'm going to analyze it as spin beam, you have a problem, because you need to put the top reinforcement at the support, right? Or your profile has to be like this, not like that, right? Depending on for prestressed concrete. So you don't oversimplify. It is always advantage to simplify, but not oversimplify. Do not generalize, but rather qualify and specific circumstance. So you cannot generalize that. You have to be very, very specific sometimes. If my weather conditions are such that the temperature is freezing, then I better be careful how I prepare concrete, how I place, how I cure. It sounds complicated, but you have to be very specific in our case. The important question is how good, not how cheap an item is. Like some people, guys who are above you in the management, and some of you will become managers one day, hopefully. But be aware, how cheap is not always good, because you may like to push the profit high and high, right? But don't get carried away. People do, they forget sometimes. We live and learn. It's always possible to increase one's knowledge. I tell you, this is my experience. I'm here in this class, part of the reason is I don't want to stop learning, right? Because you want to keep plowing the lane. Make sure, doesn't matter your age, don't be shy. Don't think that I'm 26 now. Your age, you may say, my God, I'm old. That's not old. You're just a kid, right? So depending on your perspective, always learn, right? I was fortunate enough that I picked this up early in my career. We used to have a beautiful campus at BITS Pilani. It was a temple in the middle. So I became a devotee of knowledge, basically, as we know in back home. So I pursued it through the life that knowledge is power. We know that. So knowledge is power. We need to learn. There is nothing completely new. That means you cannot reinvent the wheel. You've got to see what has already been done and improve on it, right? So that means it is a progressing thing. It's not like something that will happen in one stroke, right? Like iPhone didn't happen overnight. There were other things before that. That's what it means. So these are the principles. We are very close, but I would make sure, before I forget, there is a request that, my request, that the test be done following week. Anybody has problem? I had some difficulty with one person, so 2 weeks from now, we will have the test, not 1 week.
Yes.
Is it okay?
Yes. I mean, that's actually.
Anybody going out of town or has,
So-
or going, expecting to get sick or something, just kidding.
not next week. Not
Next week.
Oh my God.
All right. So democracy rules, unanimous vote, Barry is happy. Okay, so here's the deal. I was going to give you assignment for chapter 3, but we will cover it in next class. So that's good news, right? But we will have one assignment next week that will be due following week, and it will be included in the test. So there is a minor tune up. We won't have the whole chapter, obviously, but we will include some more material, right? So Barry has to read at home now. I'll send you the notes. Okay.